Bayes' theorem gets its name from Thomas Bayes, who was an English Presbyterian minister. The only paper he published during his lifetime was in theology, although he was intrigued by probabilities. His work in probabilities was published into a paper after his death, and people did not pay much attention to it for a long time. So what are probabilities? A probability is a measure between 0 and 1, representing the chance that an event is true. 0 means absolutely false, and 1 means absolutely true. Simple, right? Not so fast. The interpretation of probability was a major source of conflict and rivalry for centuries, and there were two major camps, the frequentists and the Bayesians, although there were others. The frequentist interpretation associates probability with random systems and defines it to be the relative frequency of an event in a large sequence of repeatable experiments. But what if the assumption of repeatability breaks down and we don't have a long sequence of repeatable experiments? Let's think in terms of bets instead. Suppose two strangers decide to arm wrestle for the first time. Who would you bet your money on? Well, you would bet on a guy whom you believe has a higher chance or probability of winning. And it is entirely possible that a friend of yours bets on the other guy because she believes the other guy has a higher probability of winning. Bayesians interpret probability as a degree of belief, which can be adjusted in light of new evidence. And different people can have different degrees of belief about the same hypothesis, which makes probability subjective. Well, here it is, Bayes' theorem. Given events A and B, we write the probability of A given B equals to the probability of B given A times the probability of A divided by the probability of B. Let's dissect the denominator using the law of total probability. Consider again events A and B. Their intersection is A and B in purple. The complement of A, or not A, is marked with diagonal lines. The law of total probability states that the probability of B equals to the probability of B and A plus the probability of B and not A, which equals to the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. And so we arrive at this formula for Bayes' theorem. Now let's use it in an example. This example is from the Handbook of Forensic Statistics, and it is about HIV screening. In general, infection with HIV is medically disqualifying for entry into military service in the U.S. All applicants typically undergo a comprehensive medical examination, including HIV screening. Suppose Anne wanted to join the military and took the ELISA HIV test as part of the medical entry exam, and that her test result was positive. The ELISA HIV test is known to be 99.7% sensitive and 98.5% specific. That is, 99.7% of those who have HIV test positive if they take the test, and 98.5% of those who do not have it test negative if they take the test. Suppose that 0.34%, or 34 in 10,000 people, have HIV in the US. What is the probability that Anne has HIV given her positive test result? Remember how we used Bayes' theorem with events A and B? We will now use it with events has HIV and gets a positive test result instead of A and B, respectively. So let's define some notation. The probability that Anne tests positive given she has HIV is the probability of a positive given HIV, which equals to 0.997. The probability that Anne tests negative given she does not have HIV is the probability of a negative given no HIV, which equals to 0.985. And the complement of that is the probability of a positive given no HIV, which is 0.015. And finally, the probability of a random person having HIV is the probability of HIV equals to 0.0034. Its complement is the probability of no HIV, which equals to 0.9966. Next, let's write Bayes' theorem for the probability of actually having HIV given a positive test result. Now let's plug in the numbers from the previous slide. Interesting, we get a probability of less than 19%. So even though the test is pretty accurate, the probability of actually being HIV positive given a positive test result is fairly small. This is because the prevalence of HIV in the population is very low. Another key assumption here is that the person being tested is chosen at random, and they did not seek testing because they felt ill. And so, in this example, the majority of positive tests from people chosen at random will be false positives.